The muscle that me and Esteban will be demonstrating is the quad, more specifically the rectus femoris section of the quad. This muscle attaches to the ilium of the pelvis. And then it runs down the femur bone, which then goes to the shin bone, which has the kneecap in between. The rectus femoris attaches up here on the ilium, comes down along, then actually attaches to the kneecap via the patella tendon, which then attaches to the tibia via a second tendon. So this red part is the rectus femoris section of the quad. The reason that we are focusing on the rectus femoris is because that is what is responsible for straightening out your leg by your knee. It will allow the leg to bend because there's more room now. Then when it constricts and the muscle becomes shorter, it no longer has the length to be bent, and your leg will straighten. As you can see, the rectus femoris acts as a third-class lever on your leg because you have the fulcrum all the way at the back, then your effort is in the middle between your fulcrum and the load, which will be around your foot when you're kicking something, which is our sport, kicking a soccer ball or football. Since torque equals force times distance, then the distance being from your fulcrum to your effort, in order to get a very high torque, you will need to have a very high force because the distance is going to be quite small. The torque times force times distance between the fulcrum and effort is actually the same as torque between the fulcrum and load, right? So these two torques are the same, but this is torque fulcrum to effort, and this is torque fulcrum to load, okay? So then distances are different and forces are different, so that is how you calculate the force that you are outputting onto the balls you're kicking. So then, in order to find the moment of inertia, right, torque also equals moment of inertia times angular acceleration. And angular acceleration equals normal acceleration divided by r. So if you find the normal acceleration by taking a video of you kicking something, right, then you can find the angular acceleration. Because you already know the torque from the above two examples, right, then you just relate that to this, find acceleration, and you can find the moment of inertia. So then, since work equals force times distance cosine theta, you can basically...
Okay, so ignore everything that I just said because it's dumb and I muted it. So basically, you take the distance that your foot moved forward, right, cosine theta, parallel to the ground, and you multiply that by the force outputted by the effort onto your leg. And that is the work that you are doing.
Hi, this is position, And velocity is change in position over time. And acceleration is change in velocity over time. And this is all related linearly. So this is in terms of a soccer ball. If it were kicked, we can see how it displaces time. It displaces position over time. But in the terms of our leg, we aren't moving in a single line. We're doing more of a curve. So then we would not be checking the change in position linearly. We would be checking the change in angle from our initial position to our final position. In the video before, we can see that I'm standing straight and my leg is bent, and it quickly switches to being straight like this. So we know that the difference is going to be, well, one's at a different angle than the other. So similarly, we can use the same equation, but we have to change it in terms of angles. And to do that, we use theta as our position. We use theta as our angle position. And then V is also going to be change in theta over time. But this is known as omega. So omega is equal to change in theta over time. Like this. So omega is a velocity, and position is theta. And omega is equal to change. The triangle means change of theta over time. And similarly, we can do the same thing for acceleration. Because acceleration is a change in velocity over time, we can describe as acceleration in terms of angles as the change in omega over time. So we'll do change So here we have alpha. Alpha is equal to the change in omega over time. This is acceleration in terms of degrees. So here our equation changed from linear to radially, where theta is the thing that we want to find. And our new introduced units are omega, which is velocity, and alpha, which is acceleration. Hi. The use of this kinematic equation is very important. In our case, we have a third class lever, where this is our knee, and we call this a fulcrum point. And then from that part, from a little bit below the knee, there is a section where the effort is applied, and that's where our muscle is connected to. And our muscle will pull upwards or it will relax, and the thing will go down. And this part is where the load is. If we're kicking a ball, the ball will be the load. Now, the use of a kinematic equation is very important because what is changing is our theta. And just like our leg, it's moving up and down, up and down. This is before the ball is kicked, and this is at contact with the ball. So change in theta will be important, because theta can change in either velocity or acceleration. And just like our leg, we can accelerate it or we can maintain it at a certain velocity. Therefore, all the points inside of our kinematic equation can be solved for in real life motion.